I don't know of any new announcements. I think you've heard them all. This is nearing the end of the first mini-term. Our volleyball team is hosting Sneed State this evening on the Birmingham West Campus, Arthur Shores Fine Arts Building, which is also our gymnasium. That's night at 6 o'clock. I'll be in class, so I won't be able to go. And then this weekend, I think that's Friday and Saturday, they'll be playing in the Wallace State Huntsville tournament up in Huntsville, Alabama, so that'll be up there. And you've heard about scholarships and NASA Community College Aerospace Scholars Program, so all those kind of things. Well, I did all that, but didn't start. Yeah, I started the recording. I thought it wasn't. Boy, it is. Okay. Any questions on anything we've done so far? Now, this example here is one we talked about before that it wasn't, the example doesn't exist. But well, no, I'm sorry. This is at the top of the page. We talked about that. Example 4, which is coming up, it does. So I think we've already discussed this one. There's, if xy is approaching 0, 0, your limit there is 1 over 0, which does not exist. So you don't have to do a thing with it. You don't have to fiddle with it. Now, oh, and they skip example 4. No wonder. Okay. Let's take a look at example 4 then. And you can also go to larsoncalculus.com and see an interactive version of this type of an example, and they probably will do a lot better job than I will be doing here, but let me get it set up to go. Show that this limit does not exist. The limit as xy is approaching 0, 0 of x squared minus y squared over x squared plus y squared. Okay. Now, our good old plug it in doesn't help us much here because what you get is 0 over 0. Okay? So that's not helpful. You can factor the numerator, but you can't factor the denominator, so there's nothing you can do with that. Except possibly this. If you factor that numerator, you get x plus y times x minus y. Okay? So, what's that?
Don't tell me long division.
Oh, let's not do that. Okay. I don't think that might be helpful either. I hadn't thought of that. It might not be a bad idea, but I don't believe so. That would be a mess. A terrible mess, I think. So, here is part of the problem here. Now, on the one hand, I look at that and say, well, that numerator, in most cases, is going to be less than the denominator because you're adding in the denominator, subtracting in the numerator. They're all always positive numbers. And you would think that it could possibly have a limit there. It doesn't look hopeful, but it doesn't. Definitely an indeterminate form. So, these kind of problems, it's sometimes useful to do this. Let's let, say, y equals 0. Okay, just let y equals 0. And then, this would be x over x would be 1. So if you're coming in the x-axis, where y is equal to 0, either direction, your limit there would be 1. Okay? But if you're coming in the y-axis, where x is equal to 0, what's your limit then? Minus 1. Well, you can't possibly have a limit coming in this way of +1 and a limit that way of -1. Remember, that's the thing about two independent variables here. The path matters. And since that threw it completely out of the window there, that limit cannot possibly exist, because coming in one direction you get a +1, another direction -1. Narrow the twain to meet. There's no way that if you think of the z being here and you're coming down the x-axis here or the x-axis from the negative direction, and you're come out at +1, that's the limit as you're coming in here. But then when you go, I'm sorry, I was doing the x-axis. Coming in this way or that way, you get a limit of +1. But if you're doing the y-axis from that way and that way, the limit's down there. No way. There is no way that those two could be equal. Now, and they don't show it here, but basically what that does, it consists of all points in the xy plane except for 0, 0. To show that the limit approaches 0, 0 does not exist, consider approaching two different paths along the x-axis, and, well, they did a different one. Along the x-axis where y is equal to 0, that gave you 1. But then they said along the line y is equal to x. So along the line y is equal to x, that goes to 0. Numerator goes to 0 and denominator goes to 2. Because I think there's something, but not 0. Okay, so then that would have a limit of 0. So if you came down this way, y is equal to x, the limit's 0. This way, the limit's 1, and that way, the limit's -1. So different routes that you take to get to the origin all give you different values.
You're saying that in this case, the path always matters.
The path matters, yeah. Yeah. And
so it doesn't matter. You coming this way or that way,
yeah.
Whatever.
Yeah.
It has to be the same way.
It has to be the same. If the limit exists, it's going to have to be the same. Oh, and Josh decided to show up today. Yeah. Oh, good. Okay. As if you ever missed today. Okay. All right. Good deal. We just finished yakking about example 4, and I did it one way, the book did it a slightly different way. The point is, different paths you come in give you different results, so the limit can't exist. Okay? I found theirs a little more bizarre, but anyway. Now I think we're ready for the next, subtopic here, continuity of a function of two variables. So we've talked about limits of functions with two variables, and the only new thing there is they're even harder to find because, as Bill was saying, the path you take matters in 2 dimensions, whereas when you got a one-dimensional plane, you can only come from the left and the right, okay? That's all, and if the limit exists, it exists. This way you can come this way, that way, this way, any kind of way, and they all have to have the same limit. Okay, so let's look then at continuity of a function with two variables. And it said, notice in example 2, way back there, here was the limit of f of xy equal 5x squared y divided by x squared plus y squared as xy approaches 1, 2 can be evaluated by direct substitution. That's how we always start to see if indeed it does. So if x is approaching 1, so that would be that, and y is approaching 2, this would be 5 times 2 is 10, divided by 1 plus 4 is 5. That would have a limit of 2. And sure enough, there it is. In such cases, the function is said to be continuous at the point 1, 2, because the limit does exist. Okay? So, pretty simple seeming definition for continuity here. And here they'll spell it out for us. Definition of continuity of a function of two variables. A function f of two variables, meaning two independent variables, is continuous at a point of x0, y0 in an open region of R, okay, region R, if f of x0, y0 is defined, one thing, and is equal to the limit of f of xy as xy approaches x0, y0. Okay? So notice what we just did in the previous one. We first just plugged it in to see if it was defined. It was, and it was a very reasonable definition, and then as x and y approach that, you were going that. That is, the limit as xy approaches x0, y0 of f of xy would be f of x0, y0. That would be, that's what it takes. That this function is defined there, that you do have, now I don't know what that vertical line is, every now and then they show up, I don't know why, and that the limit exists. That's it. Function is continuous on the open region R if it's continuous at every point in that region R. Okay? Now, what this, the function f of xy equal that is not continuous where? At 0, 0, because you can't, it's not defined there. Remember, it has to be defined at every point, and the limit has to exist at every point. Now, when you plug in 0, 0, it gives you an indeterminate form, so you don't know if the limit exists there or not, but it's not continuous there because it's not even defined there. Because the limit at this point does exist, it says, you can remove the discontinuity by defining f at 0, 0 as being equal to what the limit is there. Such a discontinuity is called removable. And we've had those before, okay? That you can plug something else in and make it work. Now, this function, it looks a lot like the function we had before, except we didn't have the square there. It's not continuous at 0, 0, and that discontinuity is non-removable. Okay? Now, the two examples I gave were y is equal to 0, that goes to 1. For x is equal to 0, this goes to 1, but when you square it, this goes to minus 1, but when you square it, that goes to 1. But that example they gave, when x equal y, this is going to 0, and this is going to 2, okay? But anyway, it's going to a positive number, and 0 over a positive number is 0. So that shows it's not continuous at 0, 0, because one way happens to be 0, the other way happens to be 1. That discontinuity is non-removable. There's just no way you can plug anything in to make it work. Okay? So, next theorem. Here's another vertical line in there. I don't know what they're doing there. Okay? Continuous functions of two variables. If k is a real number, any real number in the world, no matter how big or how small, f of xy and g of xy are continuous at x0, y0. Both of these functions are continuous there. then the following functions are also continuous at x0, y0. Any scalar multiple of either function, k times f or k times g. If both of these are continuous there, just multiplying by a scalar will keep them being continuous there. The sum of the difference. If both of these are continuous at x0, y0, the sum, f plus g, or the difference, f minus g, or g minus f. They're all continuous at the first two are. The product, fg, is also continuous. Okay? So we've got sum, difference, and product. The quotient is also continuous there as long as g of x0, y0 is not 0. Okay? In other words, you still can't divide by 0. So if g is a non-zero value at x0, y0, then the quotient function is also continuous. That establishes continuity of all your polynomial and rational functions at every point in their domains. Of course, if g was 0, it would be in the domain. Okay, so just remember that. Furthermore, the continuity of other types of functions can be extended naturally from 1 to 2 variables. Big statement there, without proof, but we'll take your word for it. All right. For instance, the functions whose graphs shown here, figure 1323 and 1324, are continuous at every point in the plane. Okay. When I first looked at this, I thought, what in the world is that? That's where it's going. It's so hard to picture this because it's a three-dimensional thing in 2 dimensions. I think what this is the lip folds up here, and it's folding up there too. I just don't know what that line that goes across like that is. Because obviously, or it sure looks to me like it's sinking here, so it can't be rising at the same place it's sinking. But I think this is just where it folds up there. But why in the world do you have that bar there? That seems to be continuous everywhere in the plane. Now, you certainly can't see every point in the plane, but the ones that are shown here. Oh, here's the function. The surface is 1/2 the sine of x squared plus y squared. See, sure enough, it's 0 at 0, 0. And that, yeah.
Come down, start at the top of that rim. Is that the sine period?
Yeah, as far as I can tell, it's starting at 0 and going up. I just don't see where it ever goes negative, but it seems like it would have to because sine is negative even when you have a positive argument of sine. And I just can't see, well, maybe it's going negative in this direction, and then going positive in that direction. I can't even figure out what they're saying. Yeah, that's what it looks like. This is going down this way, and it must be coming up that way there. But the figure here isn't helping me. Here is what is helping me. Sine is a continuous function everywhere. Okay? So it really doesn't matter if they got the drawing right. I was just focusing on the drawing at first. This is what says it's continuous. Whatever your argument is here, the sine is continuous everywhere. Sine of just the positive values are continuous everywhere. And taking half of a continuous function is continuous everywhere. Okay, so yeah, we're okay there. This one, I'll mess with the graph at first. Let's take a look. What is missing? I asked my work study student to clean the boards this morning, but she did everybody's but mine. I don't know why. Okay. I think I do know why. there was a class in here. She probably got started too slow, or not. She was working on the other one. By the time she got here, the class was here. That's what. Okay, so here's another surface. Okay. Who cares what the surface looks like? Cosine function, continuous everywhere. The squaring function is continuous everywhere. The cosine function is continuous everywhere. Exponential function is continuous everywhere. Of course, the square root function is not continuous where if the argument is negative. The x squared plus y squared is never negative. So that has no limits on it either. So yeah, this is continuous everywhere because all the functions involved are continuous given the values that you're dealing with. Now, when y is equal to 0, cosine is 1. And exponential would be 1, 2. But at 0, 0 it would be, because this would be 0. Each of the 0 is 1. This would be 1. So yeah. So at this point here, we know it's 1. And then some of the other points you can fiddle with and see what you got. I don't think it ever gets to 0. Doesn't seem like it would. Ever gets to 0 or negative. So beats me how they drew it, but looking at this, you can tell it's continuous everywhere. Okay. Theorem 13.2, which is basically what we were just looking at, continuity of a composite function. If h is continuous at x0, y0, and g is continuous at the value for h at x0, y0, then the composite function given by g composed with h of x0 of xy is equal to g of h of xy, and that's continuous at x0, y0. That is the limit as xy approaches x0, y0 of g of h of xy is g of h of x0, y0. If this is continuous there, okay, h is continuous there, and g of h is continuous there, then the limit exists. Notice in this theorem that h is a function of two variables, g is a function of one and only one variable. Whatever the output for h is, that's what g's input is. So g is a function of one variable, h. And whereas you learned before that the composition of two functions is not necessarily commutative, it can't be commutative here because you can't do a g dot composed with h because g is a function of one variable and it has one output. H has input of two variables. You don't have two variables to do, so you can only go one way with this. Single variable function here, double variable. Okay. So, discuss the continuity of each function. F of x, y here, the A. Or it's not at 0, 0. Everywhere else that would be continuous. Okay? Everywhere else except at 0, 0. Okay? How about G?
Well, still not at 0, 0.
Okay, 0, 0 certainly wouldn't be continuous there. 1, 1 it wouldn't be continuous. Here's the sort of the quick and dirty way of doing this. What do we know? We know that y minus x squared cannot equal 0, right? So this says that y cannot equal x squared, which if you add x squared to both sides. Well, what is y is equal to x squared? What is that?
That's an old parabola.
It's a parabola. So everywhere on that parabola, this does not exist there. So it exists everywhere off the parabola, but not on that parabola. Your standard parent function parabola there through the origin, like you said. All right, here's Corey. Perfect attendance again. Way to go. Okay. That would be continuous everywhere except on that parabola. Now, let's see if... Okay. The first one of those, because a rational function is continuous at every point in the domain, you can conclude that f is continuous at every point in the xy plane except at 0, 0. And that's exactly what we saw. Or what we said. What we're doing is, Corey, is continuity of this function here. It's hard to read from back there, I'm sure. F of xy is equal to x minus 2y, who cares what the numerator is, over x squared plus y squared. That's continuous everywhere except when that denominator is equal to 0, which is 0, 0. It's the only place it can use 0. Now, I never would have plotted it this way. I never would have tried to plot it. But you see, as x approaches 0 from as x and y both approach 0 from, it looks like the negative side, where y is negative. Yeah. Is that right? Yeah. When y is negative, anytime y is negative, this thing is positive. And this thing is getting very, very small, but always positive, so that means the number here is exploding positive, getting very, very big positive. But if y is negative, and everywhere where y is positive, y is positive, everywhere where it's positive, this is approaching, this is positive, that's positive, no, I'm sorry. Well, y is positive, and x is small enough, let's just keep it that way. X is relatively small, and y is positive, then this thing is negative, the numerator is negative, the denominator is incredibly, as it approaches 0, 0, it's very negative. So, it's positive, okay? And you're dividing by a tiny number, and the quotient will be negative then. So, there is no limit when one's going up and the other's going down. Can't possibly do that. Every other value, you can actually calculate what it is. It may be an extraordinarily large or small number, but you can evaluate them everywhere except at 0, 0. That's going to positive infinity. This is going to negative. Not continuous at the origin. You can look at this and know it's not. Okay. The B part, the function g of x equal 2 over y minus x squared is continuous except at the points where the denominator is 0. At those points, given by that equation, you would conclude that the function is continuous at all points except those lying on the parabola y is equal to x squared. Now they do a pretty clever thing of showing what that looks like here, and this is pretty incredible. When y is less than x squared, this thing is very negative, and it's going down that way. Y is less than x squared is outside the parabola. Y equal x squared is the parabola. Not going to happen there, okay? But when x squared is less than y, then you're going to be positive numbers. and that's going to give you the values up here. So all the values inside that parabola, you're going to have values up here. Outside the parabola, everything outside the parabola is going to be negative. So it's heading downhill as you get close to this. This is heading uphill as you approach this. So this is going positive infinity, these are going to negative. So G is not continuous anywhere on the parabola. So it's not just that they have a little discontinuity there. I mean, it's an impossible discontinuity there. Definitely not, what would they say, replaceable, or what was the term they were using before? Removable. I couldn't think of the term. That's a pretty incredible drawing. I would not have wanted to draw it any way, shape, or form. Okay. You don't have to draw the pictures to test for the continuity there. Sometimes they help to see what is happening there, but who? All right, outside the parabola, the surface lies below the xy plane, negative. Inside the parabola, it lies above the xy plane. All right. And then, continuity of a function of three variables. Ugh. Getting worse, but it's okay. The definitions of limits and continuity can be extended to the function of three or more variables, and when they say this, they mean independent variables, by considering the points x, y, z within the open sphere. Now this is, when they say an open sphere, that means the surface of the sphere is not included, but all the points inside are included. And that would be x minus x0, where x0, y0, z0 is the center of the sphere, plus x, y minus y0 squared plus z minus z0 squared is less than whatever your delta is. The delta will be the radius of that sphere, okay? Lowercase delta. The radius of the sphere is delta, and the sphere is centered at x0, y0, 0. Okay? So now, that is your domain. Before we were using a region of the xy plane. Now we're using, in a sense, a region of space. Everything inside the open sphere in space. And then, where do you put your function? When you determine what it is, you don't have another dimension to draw it in. But this is all dealing with the domain of that. Everything has to be coming from inside there, and then the output, where do you put it? I don't know. Okay. A point x0, y0, z0 in a region R in space is an interior point of R if there exists a delta sphere about that point x0, y0, z0 that lies entirely in that region R. Now this is a three-dimensional region, not a planar region, three-dimensional region. If every point in R is an interior point, then R is said to be an open just that region is an open region. Okay. So, definition of continuity of a function of three variables. Function f of three variables is continuous at every point x0, y0, 0 in an open region R if, number one, that f of x0, y0, z0 is defined. If you can define it, it's good. And then secondly, then it's equal to the limit of x0, y, f of x0, y0, 0, z, f of x, y, z as x, y, z approaches x0, y0, and z0. So if that limit, okay, number one, for the limit to exist, it has to be defined there. And if it is defined there and that is the limit, then it's continuous. Okay, function f is continuous in the open region R if it's continuous at every point in R. There are no points where discontinuity would occur. So let's discuss the continuity of this one. What would you think? What's the little trick you do?
Well, first, I would say make x squared plus y squared greater than z.
Okay, exactly. But doing what we did, and doing exactly what you said, x squared plus y squared minus z. That's in the denominator, so therefore it cannot equal 0. Okay, because the denominator cannot equal 0. Then, what you just said, that x squared plus y squared cannot equal z. Okay, so x squared plus y squared, well, let's say it this way. If that were equal, what would that be?
0, 0.
A what?
0, 0.
No, but if this thing, if you had an equal sign there, what would that describe?
Well, z would be a circle.
Okay, yeah, at any space z, you'd have a circle of that radius, or a square root of z radius, right? Okay, and at 0, 0, it would be 0. So what is that forming? It's not a cylinder, because down here at 0, it's 0. At just a little above 0, it's a tiny little radius. And then as you get bigger, the radius gets bigger and bigger and bigger, right? As you go up. So what is it? A what?
A cone?
Not quite a cone.
No,
paraboloid. Paraboloid. That's what it is. It's a paraboloid. Because that would be a parabola if that was equal. That would be a parabola. That would be a parabola. And that would be a circle. So it's actually a circular paraboloid. We would call it elliptical paraboloid because the circle is a special case of ellipse. But that's it. So anywhere on that paraboloid, not defined. So everywhere else it would be. Inside the paraboloid, inside the barrel, the tank, whatever that thing is, you would call it, z would be greater than x squared plus y squared. So that would be negative. That would be down here. And everywhere outside that paraboloid, that would be the x squared plus y squared. The z would be less than x squared plus y squared, I think. I think I'm doing that right. So there it would be positive. So everywhere inside the paraboloid would be a negative number. Is that right? Outside it would be, well, you can't picture it because it's not there. We've already taken up all 3 dimensions with the paraboloid, but the values inside that were x squared plus y squared.
And that would be negative. Well, we just talked about half of it.
Yeah. So yeah, let's like you said, let's go up to z is equal to 2. Well, let's say z is equal to 4. That's going to be easy. Then the circle would be x squared plus y squared is equal to 2 squared. Okay? That would be a radius 2. And any z less than that would be inside that, and any z greater than that would be outside of that. And the z's, greater z's would make that negative, and lesser z's would make it positive. So I guess inside that would be positive, outside would be negative. I said it backwards before. Okay, I think so. Let's see what they say. Let's not beat the horse to death yet. The function is continuous except at the points at which the denominator is 0, which are given by this equation, which is what I wrote down too. And so f is continuous at every point in space except the points on the paraboloid. Z is equal to x squared plus y squared. And that's all they say, okay? So we didn't need to talk about whether they're positive and negative. They're just anywhere but that. Okay. So I took it further than they were intending. Should pay attention. Okay. Homework exercises for 13.2 would include either 3 or 5. They're both at Calc Chat. 5's at Calc View. Either 7 or 9. They're both at Calc Chat. Any of the odds 11 through 21. They're all at Calc Chat. 15's at Calc View. 25 to 35, they're all at Calc Chat. 27's at Calc View. You can explore doing 37 and or think about doing 39. They should both be at Calc Chat. 41 should be at Calc Chat. Either 43 or 45 should be at Calc Chat. 47 should be at Calc Chat. 49 should be at Calc Chat. Whoa, get into polar coordinates here. 51 to 55 should be at Calc Chat. 57 and or 59 should be at Calc Chat. Any of the odds 61 to 65 should be at Calc Chat. 61's at Calc View. 67 and or 69 are at Calc Chat. Any of the odds 71 to 75 are at Calc Chat. 77's at Calc Chat. 79 and 81 are true false. They should be at Calc Chat. And then 83 is finding a limit, and 85 is a proof. All right. Finally, we're through with the preliminary. Let's move on. Any questions before we leave 13.2? Okay. So let's go on to 13.3. Okay. Go from current slide, which is Chapter 13, Functions of Several Variables. And 13.3, finally getting to do some real calculus here, it feels like, and that is 13.3 is partial derivatives. So we'll find and use partial derivatives of a function of two variables. We'll find and use partial derivatives of a function of 3 or more variables. We'll find higher order partial derivatives of a function of 2 or 3 variables. Okay? So we'll do first partials here, and then second and higher partials there. Okay. So let's start with partial derivatives of a function of 2 independent variables. Okay? You can determine the rate of change of a function with respect to one of its several independent variables. Now what that means, you look at how the function is changing with respect to just one of the independent variables. And in so doing, you hold the other variables to be constant. Doesn't matter what, but you hold them to be constant. That process is called partial differentiation because you're only taking the derivative to one variable at a time. You can't take them all at once. You do it one at a time. The result is referred to as partial derivative of f with respect to the chosen independent variable. You just don't even mess with the others. They just hang around there until you need them, and then you do whatever else you need to do with them. All right. Did y'all need that up a little longer? I don't maybe too fast. You okay? Okay. Now, here's a definition of partial derivatives of a function of 2 independent variables. So if z, that is your dependent variable, is some function of x and y, those are your independent variables, then the first partial derivatives of f with respect to x and then with respect to y are the functions, and we give them this name, f subscript x and f subscript y. Okay? We don't use primes anymore because you can't tell which one you're talking about. So what you use is the subscript, and you say which variable it is you're taking the partial with respect to. So here's your definition for f sub x. The partial of f with respect to x and only x. That would be the limit as your d delta x is approaching 0 of f of x plus delta x, y, minus f of x, y, divided by delta x. Okay? Notice the y's are not part of the problem here. They're there, but you don't do a thing to them. You only let the x go from x to x plus delta x. That's the change of f from those two values, y's being the same. Whatever your y is, leave it there, divided by that amount of change of x. Okay? Which is, if y wasn't there, that would just be the derivative with respect to x. Okay? Your f sub y, or the partial of f with respect to y, is the limit as your delta y approaches 0 of f of x, y plus delta y minus f of x, y. So in other words, leave the x's alone. They just are there. They're only there. You're not changing them. You're letting y change from y to y plus delta y, and then you divide by that amount of change, your delta y. And that's your partial with respect to y. So basically, wherever you were up here on the y-axis, let's say you're right here. You're at this point right here. Okay? The partial with respect to x would be let your x change here, keeping the y the same. And that could be like this, it could be like this, it could be anything like that. It could be constant, whatever. Here, you did that same point here. Now, you're seeing what it changed. Keep the x constant and see what the change of y is. So that's the partial with respect to y. This is the partial with respect to x. This would be going down, or that was going up. Any kind of combination could be happening there. Okay? Now that definition indicates that if z is equal to f of xy, then to find f sub x, you consider y constant, differentiate only with respect to x. Similarly, to find f sub y, as the partial of f with respect to the second independent variable y, consider x constant and differentiate only with respect to y. Y'all have been doing that in your differential equations course. So let's do example 1. Find f sub x, or the partial of f with respect to x, for f of xy equal 3x minus x squared y squared plus 2x cubed y. So let's do it. Let me get my pen back. Okay. What is your f sub x? It's also a function of x and y. Okay. What would that be? 3. Right. Say again.
3
minus 2x y squared plus. I'm sorry? Oh, the screen left. Okay, come on back. I couldn't make out what you were saying. So that doesn't sound like a 6 to me. Okay.
Plus 6x squared.
X squared y. Perfect. Exactly. To find f sub x of that thing, just treat that y like it's a constant, like it was 3 or 2 or minus 1. Treat it like a constant. Take the derivative with respect to x only. And just keep the others the same. Okay? Let's do the same. They don't say to yet, but let's do f sub y. A little louder.
0 minus.
Okay, 0 minus. Okay, got it. Okay, minus. Now we're doing of this one, not of the one above it. Right. 2x squared y. Why not? Plus 2x cubed. That's it. That's your f, the partial of f with respect to y. Okay, for any value x, y. Okay, first one was 3 minus 2x y squared, got it, plus 6x squared y. F sub y is minus 2x squared y plus 2x cubed. Perfect. Okay. Let's just see how they did it. F sub x is exactly what we got. And to find f sub y, we consider x to be a constant and differentiate only with respect to y. F sub y is minus 2x squared y plus 2x cubed. All right. Starting last weekend or sometime, I think it must have been Friday, I had a sore throat, and then it got better. And now I don't know, is it what's happening outside? I don't know what it is. Now the throat's getting sore again, and I don't know why, but I don't feel sick or anything, so I hope it's just whatever's outside. Thing is, I've never been very allergic to much, but I guess at old age things changes. So let's do f sub. I think they left off an f there, didn't they? Yeah, there's supposed to be an f right here. Find f sub x for f of xy equal log x sine x squared y. That couldn't be just ordered pair xy. It's f of xy. So let's do f sub x. All right, this looks like a lot more fun, doesn't it? What would you have to do? Second? Product rule, you're absolutely right. And how does that go? ln of x, you're going to do the first times cosine of
sine squared x y.
No, the cosine of x squared y times chain rule 2xy. That's it. Okay? Do you see that? Okay? I think they're next going to ask us to do f sub y of xy. Huh? Oh, yeah, you didn't. You did, you? Okay, go on and finish. Sine of x squared y over x. That's it. That's all you have to do. Sorry about that. Okay? Now let's do the partial of f with respect to y of your f function, not your f sub x, but f. What you reckon this is?
Do you still do the product rule and just count it as 0?
Well, the first one would be 0, so you don't have to do anything with it. Just treat that, but if x is a constant, log x is a constant, right? So just treat it like a constant. That would be log x times cosine of x squared y times x squared. Yep. Okay. You have to keep the argument with it. You know, chain rule. Take the derivative of the outer function, that's cosine, of the whole thing, and then the derivative of the inside with respect to y, and that'll just be x squared. Okay. Let's see how they did. Well, I think, okay. If you look carefully, you can see we got all the pieces there. It's just hard to read, so I'm going to go on. I'm going to put up the other one 2, and that's hard to read too, but log x cosine x squared, yeah. Okay, now I'm going to erase it so you can see the answers a little bit better. But we got the same thing. To do the partial with respect to x, treating the y's as if they're constant. This is the product rule. So it's the, as you did, the first times derivative of the second. Derivative of sine squared 2x is cosine sine x squared y is cosine x squared y. Then time derivative of this with respect to x is a 2xy. That's your first time derivative of the second. Now your second time derivative of the first. Derivative of the first is 1 over x, and there's your second. So put that on top of the x. Find f sub y, consider x to be a constant and differentiate with respect to y. That's a constant, that's a constant. So you're only differentiating basically sine y. So your coefficient in front is a log x. That's what it basically turns out being. And then the derivative of sine is cosine x squared y. The derivative of the chain rule, the derivative of the inner part, is just x squared. That's what we got. No chain rule necessary, no product rule necessary, because the product rule would then be the derivative of the first, which is 0, times the second. 0 times sine is still 0, so it doesn't contribute the thing. Okay. And by the way, they have a picture here of Jean Laurent d'Alembert, or something like that. The partial derivatives came after Newton and Leibniz by several years. Between 1730 and 1760, Euler and d'Alembert separately published several papers on dynamics in which they established much of the theory of partial derivatives. I hate to say this, but I will. I enjoy saying physics sometimes drives math. Math certainly, physics uses math like crazy, but sometimes it drives it. We need to do this. How can we get the math to do it for us? And that is indeed what. Sometimes who's on first, who's on second, it's not real clear. So anyway, that's the character there. If you haven't chosen a potential paper topic, if you take a look at that, there's Newton's mentioned, Leibniz is mentioned, Euler is mentioned, and d'Alembert is mentioned. And then dynamics, partial derivatives are certainly mentioned, equilibrium, fluid motion, vibrating strings. There's a whole bunch of potential topics there. All right. Now, do you remember back when you first started doing derivatives? Maybe or maybe not. But if you do, did you recall it all? Somehow it gets somewhat confusing because you had so many ways to talk about it. You do f prime, you could do y prime, you could do df dx or dy dx. You could do just all these different ways of saying the same thing, right? Partials, just about as bad, possibly even worse. But let's see. There is one aspect that is a little worse, I think. You just have to get used to it, or think through what it's doing. Here's the notation for first partial derivative. So for z is equal to f of xy. The partial derivative that we've been calling f sub x, that's the partial of f with respect to x, the first variable, and f sub y, which is partial of f with respect to the second variable, y, also can be denoted this way. Either the d's got a lot messier, or that's actually a different symbol. And I don't know what that symbol actually is, so I just call it partial with respect to x of f of xy. Or you could have put it partial of f, and you could have left off or put of xy over partial of x. That's partial with respect to x of that. And that is your name like we did before, f sub x of xy. Or you could call that z sub x of xy, partial of z with respect to x. Or you could call it the partial of z with respect to x. Okay? So just like before, we have 4 different ways of saying the same thing. So get used to it. And the partial with respect to y of alpha of x, y, L sub y of alpha of x, y, z sub y of alpha, or partial of z with respect to y. So whenever you see the crooked little d-looking things, that's partial. So I don't call it d's anymore, I say partial. Partial.
Can we call it the curly D?
Curly D is fine, okay?
That's the first time I heard it, that's what they call it.
Wasn't that when you were at school?
First time I heard it, they called it curly D.
Curly D, okay. I hadn't heard that, but that's a great name for it. I wish I had heard that before. I think I would like that. Just like the Indian student called me Gibbity. Yeah.
Oh,
Yeah.
DYDX?
Yeah. DBDX, you know, I thought, what is he saying the first time he said that? Because he talks so fast. The first partials evaluated at a point AB are then denoted partial of z with respect to x at AB. Okay? So in other words, you take the partial of the variables, and then after you take the partial, plug it into AB. Don't plug into AB first and then try to take the partial. It's always going to be 0 because you've already evaluated everything. Or the partial, or curly dz by curly dy, or whatever you want to
So
call
I
it.
Googled it. It's a lowercase delta.
Is it a lowercase
That's
delta?
what it says, but I didn't know it was.
I thought that
Symbols
symbol like
that-
that was a delta.
Yeah, that,
The triangle
Yeah.
is a delta, and then I guess that's lowercase.
but the lowercase should look like an S.
Yeah, it looks like that. The one that we just had is the radius of that sphere. That was the delta.
Maybe I thought it was one thing.
Yeah.
I don't know.
Yeah. But anyway, whatever. I like curly D. Okay. But I'm so used to calling it partial, I'll forget to call it curly D. I have to stop and think about that one. All right. Partial derivatives of a function of 2 variables, z is equal to f of x, y, have a useful geometric interpretation. This is what I was already arm waving at you. If y is equal to some constant y0, then the partial of z with then z, when z is equal to f of x at y0, f of x comma y0, represents a curved, not the surface, but the curve form by intersecting the surface z of f of x, y with the plane y equal y0. And here's what we've got. Here is your function. The red looking thing is your function. That's your z as a function of x and y. Okay? Now, the partial of f or z with respect to x would be any y, you would take this thing. But if you choose that plane y is equal to y0, now the x-axis coming this way, y-axis going this way, we're going to use y0 being positive here, and that's that plane right there. Then the portion of that surface that is your z surface, your f surface, that portion where it cuts that plane y is equal to y0, that gives you a curve, and then the partial there is simply the first derivative of that curve. Okay? The d by d, not the curly d by d, curly d. Okay? And that's how you define it. So that's your sort of geometric interpretation of my arm waving here, you know, the slope at that one value. That's what you got here. Okay. Therefore, f sub x of x0, y0, this is just going to be a number, okay, but that would be basically the slope of f when y0 is a constant, and that curve that would be the slope of the curve at the point x0 along that curve, okay? The limit is the delta x is approaching 0, f of x0 plus delta x, comma y0 minus f of x0 y0 divided by delta x. So in other words, you keep your y0s constant at y0, and you increase your x0 just a little bit to see what kind of a slope you have going there when you divide it by delta x. Represent the slope of that curve at the point x0, y0, and then z0, which is the f value at x0, y0. Notice that both the curve and the tangent line lie in the plane y is equal to y0. They've got to, okay? I don't know why that's a specific note, but it certainly is true.
Well,
Oh, yeah.
okay, we're gonna do this for all three of them, but wave your arms a little bit for me. We're saying whatever plane it's in, we want a tangent at that point.
At that point, in that plane, yeah.
And okay, now we're gonna change it over and come into this plane
Right.
or something.
Yeah, and then we're going to do it there.
And then we'll do another one
Right.
here. Now, what about?
Okay, you see the z here is your independent, is your dependent variable.
Oh,
These are the only two independent. So
okay, it's those two. Now, putting those together, are we gonna get an intersection or anything?
well, they would all intersect at that point x0, y0, z0. That would, yeah, that's just the only place they can.
Okay.
Now, I think what you're thinking about is what we're going to get to a little bit later, called a gradient, which is going to give you the, if you have a surface there, okay, whatever that surface is doing, then your gradient is going to take the partial of one and the partial of the other and give you the direction of maximum steepness or minimum steepness. And so in a sense, we're heading that direction. We're not there yet.
Well, I wasn't there.
Oh, that's not where you're heading. Okay, all right. But that sort of is coming up, maybe in a sense. All right. And there's, similarly, I don't know. Okay. Similarly, if you took the partial of alpha with respect to y at x0, y0, again, you take the partial at xy and then evaluate it at x0, y0, and that would be the limit as that delta y is approaching 0 of alpha of x0. That's not changing, comma, y0 plus delta y minus alpha of x0, comma, y0. So you're only taking the difference in your function, your z function, that when y changes, leaving x constant. So in other words, come out some distance here from the x-axis parallel to the xy to the yz plane. Come out x units here. That's your x0 here, and that intersects that same curve, that same surface in a curve that's along that plane x equal x0, and then that curve that plane intersects, then the slope there, and this happens to be going downhill there. Going this way, I think it's going, no, you're going, you should remember this is positive x, that's positive y, so that's the one thing that the graphs sometimes throw me off a little bit because I think we're going positive that way. No, that's negative, come this way. Represents the slope of the curve given the intersection of z and the plane x equal x0. Okay? At the point x0, y0, z0. See, this is the dependent variable depending on that x0 and that y0. That's what you see turns out to be. So there they put it as x0, y0. Here they call it z. Up here they call it z0. Okay. This is exactly that. Okay. Informally, the values of partial of alpha with respect to x and partial of alpha with respect to y are curly d alpha over curly d x and whatever. At the point x0, y0, 0, z0, denote the slopes of the surface in the x direction, then the y directions, respectively. Nothing that sort of combines the two yet, okay? So that would be your, you just do them each individually, separately. Here's example. I think we skipped example 2, didn't we? Yes, we did. So let's back up. That's actually not a bad place to do example 2. Actually, we should have done example 2 before we did that slide, because that paragraph, little bitty paragraph at the bottom of the page is after example 2. But let's do example 2 first. Here's your f of xy. Okay. X e to the x squared y. It says find f sub x. How do you reckon you're going to do that? Product rule again. So how does that go? X e to the x squared y, 2x and y. Okay, perfect. Now I would rewrite that slightly to be 2x squared y e to the x squared y. Right? Because these things are all multiplied together. Go and put your 2 out front. The 2 x's together make the x squared, the y out front. You could have done the other side of v. But I like to always put it on the front side of v because sometimes my writing's a little sloppy and I don't know if I've got it as part of the argument of v or not. So that helps me see it. Now, that's just the first part of it. I almost skipped and forgot to do the second part of it. I probably shouldn't have done this yet. Then let's hold off on this one. I keep forgetting to do the second part of the product rule. What is the second part? Plus e to the x squared y. Okay. Because the derivative of the first is that. Okay. Now let's clean that up and make it 2x squared y e to the x squared y plus e to the x squared y. Which, if you wanted to take it another step and factor out the e to the x squared y, then you have 2x squared y plus 1. There's no reason to. It's just another way to write it. Now, when I was doing my Cal 2 class earlier today, there were a lot of problems that you could have written, well, in calculus. There's usually tons of different ways you can write any given answer. And this is just one small example of how it can have several different things. And I do have the codes for you if any of you want to use WebAssign. I just haven't gotten around to putting them out there on Blackboard yet. I started going through emails this morning, trying to find them, and I kept hitting emails that were bombs, and then they blew up on me, and I had to do other things before I could leave that email to do something else. That's why I hate looking at emails. There's always so much out there that someone's expecting of you, and I just better not to know, isn't it? No, I'm sorry, that's not true. All right, now let's do our f sub y of xy. And what would that be? X
e to the x squared y, and we're going to do the upper part that we 2x.
No. With respect to y, not x.
Yeah, I'm saying just the upper part of it.
Yeah. But you take the derivative of that with respect to y, not with respect to x. What is the derivative of that upper part? With respect to y. x squared. So that makes this an x cubed. Now the y is gone then. Okay. I probably didn't have to take that shortcut. Oops. Okay. If this is helpful, I'll do it. Times derivative of the upper part is x squared, which then there is no product rule involved because there's no y only shows up in that one place. So what I think of, treat this like the coefficient of e, and this is the coefficient of y. Okay, so it's this coefficient times e times this coefficient. Okay, and so that would be x cubed e to the x squared y. Okay. Oh, I didn't read the whole problem, did I? It says for f of x equal that, find f sub x and f sub y. We've done both of those. And evaluate each point, or each of these, at the point 1 log 2. We should have done it a little differently now, but let's do it. F sub x of 1 log 2. Log 2 is just a number, just a weird way to express it. So what would that be? Let's go straight to our answer. Now, which answer did they use? They left it. They didn't combine. Okay. Let me make sure I've got the same. Oh, they left it in a weird form. Let's use this form right here. Plug and chug. What do you get? Two log 2 e to the log 2. No, I'll plug in the 2. Log 2 plus e to the ln 2. All right. Now, what is e to the ln 2? 2. So this would be 2 times 2. That would be 4 log 2 plus 2. Which you could say, if you wanted to, 2 times ln 2 plus 1. You don't have to. But that's what you would have gotten kind of, sort of, if you'd have done the other. I don't know. Okay. That's our answer. 4 log 2 plus 2. Okay. I don't have room at the bottom here, so let's go over to the side to do our f sub y. F sub y of 1 log 2 is equal to what? And let's use this one. I should have just gone to the side here. E to the log 2, which is 2. Perfect. That's all there is to it. All right, good deal. Now, that's where the next, well, we've already done those, okay? So now we're ready for example 3. How are we doing on time? I think we got time. Oh, yeah. Find the slopes in the x direction and in the y direction of the surface this, at the point 1/2, 1, 2. Time out. I'm a cynic. I don't want to waste my time doing a problem that's ill-posed. In other words, it can't happen. So I always like to plug in and see if we really get it. That 1/2 represents the x. So 1/2 squared would be 1/4, and 1/2 of 1/4 is 1/8. So this would be a minus 1/8 minus 1, so that's minus 9/8 plus 25/8 minus 9/8 plus 25/8? 16/8, which is 2. Yes, that is correct. Okay. So, at least we know that point is on that curve. Okay, so find the slopes in the x direction and the y direction of that surface. What will give you the slope there? In the x direction? F sub x, the partial of x with f with respect to x. If you haven't noticed it, I like the subscript notation. It's easy to write. Curly D's are fun to say, but they're harder to write.
I'll look it up again, and curly D is actually a thing that's called.
Is that right?
We're not just making.
Yeah, they do call it curly D. Good. I may have heard that before. I just forgot it. Okay. I'm surprised. I usually remember trivia like that. I don't remember important things. I remember. Okay. Go ahead. What's that partial of f with respect to x? Negative x. Perfect. Yeah, that's it. Okay. So what is the partial of f at 1/2 1? Because it's only the xy. What's that then? Negative 1/2. Perfect. Okay. Now let's do the slope in the negative in the y direction. I got negative on the brain here. F sub y at xy is equal to negative 2y. So F sub y at 1/2 1 would be negative 2. Okay, so that says in the x direction, whatever that curve is, in the x direction, it's going down slightly, a slope of minus 1/2, but in the negative y direction, it's going down pretty steeply, negative 2. So going downhill, both sides, but going downhill slowly here and rapidly there.
Yeah, what we're saying, we just separate these things for the, say, the x direction and then the y direction. We don't care about the.
We don't care about anything in between, right? We're just focusing on those. And we were up at 2, so it had room to go downhill both ways before it went negative. Let's see how they did it here. Let me delete what I did. Hang on to what we got. Well, we got this part. Partial of f with respect to x was minus x, and partial of f with respect to y is minus 2y. Got that. And in the x direction, that slope is minus 1/2, yes. And in the y direction, that slope is minus 2. And let's go back to our function here. And we could have even named that function, couldn't we? This function is this is z. Z is equal to minus that, and then it's got a plus over here. All that is an elevation. Okay? What would this represent? Okay, not quite a circle, but ellipse.
Yeah. Oh, that's right.
Yeah. And this, that would have been elliptic parabola, only it's going to be downward because that's going down and that's going down. And this just elevates it up, so you're starting your vertex is up here at 25/8, which is just over 3 and an 8. Okay. So this is how it looks. This is that part. This is just part of that elliptic paraboloid. Okay. And notice here it's going up 3 and an 8. 1, 2, 3 and an 8. And then it's coming down in both directions. And that's why the slopes were down in both directions. In the x direction, whoa, that is supposed to be a negative 1/2. That looks pretty steep for a negative 1/2. Of course, you got this weird perspective on it anyway. But this, yeah, that is a lot steeper than that, and that's -2 in that direction. So, the elliptic parabola. I was going to point out to you what they were here, but it's not a good way to talk about it, because except that your x is your major axis and y is your minor axis, and this is about twice as far out. This is between 2 and 3, not twice as far out, and this is between 1 and 2. Sort of makes sense. Slope, really steep slope. All right, example 3. They're skipping 4 and 5. I want to see if we can maybe get 4 done. I don't know if we have time or not, do we? Yeah, 8 minutes. Let's see what we can do. Find the slopes of the surface f of xy. Ooh, okay. F of xy is equal to 1 minus x squared minus 1, no, x minus 1 squared minus y minus 2 squared. Okay, at the point 1. Okay, again, cynic that I am, I want to make sure this point is indeed on this surface. Let's see if it is. When x is 1, this is
1.5.
Is it 1.5? It's 0. Okay, this one's 0, and when y is,
Oh, my bad. I was looking at
oh yeah, don't look at that. Yeah, when y is 2, that's 0. So yeah, z is equal to 1. Yeah. Okay, we're on it. Okay. Now, we're to do the same thing. It says find the slopes of the surface. So let's do our f sub x at xy. And what does that give us? -2 times x minus 1. Done, right? Okay. And our f sub y at xy is equal to -2 y minus 2. Done there too. So let's evaluate this f sub x at 1, 2. And of course there is no y in it, and this would be what? 0. And f sub y at 1, 2 would be 0 also. Well, as you sort of, I hope.
Test question.
Huh?
That's a test question, right?
Oh, you think so?
Yeah, it should
Okay. If you think about it, I was going to ask ahead of time, but I thought they'll give it away. What is this describing here? It's a lot like we had before. That is, you know, you made up new things like
It's the ellipse.
elliptic parabola again. Okay? Because that's, except the thing is, this is centered at 1, 2. And look at this, you're at 1, 2. And where are you here? You're elevated up 1. Yeah, there's 1. You're at the vertex of this elliptic parabola that's down here. So sure, your slope's 0. You're at the very point. So everything is 0 there. And I wish if you look in your book, you'll see the illustration of that. Okay? You're at the vertex of that because you're at the point 1, 2, which is your displace, your axis is there, and you're 1 point up. So yeah, you're right there on the money. All right. I think that ate up the time, didn't it? Once upon a time, I had a pencil out here. I think I must have put it back. Yes, I did. So, we'll start with example 5 next time. Let me erase this so I won't have 2 marks on the same page. All right, let's see if we got far enough along to have any homework exercises here. I think you can do any of the odds 5 through 9. They should all be at Calc Chat. I think you can do any of the odds 11 through 39. Okay, a lot there. They should all be at Calc Chat. 13's at Calc View. I think you can do 41 or 43. They're both at Calc Chat. 41's at Calc View. I think you can do 45 to 51. They're all at Calc Chat. 45's at Calc View. And then you can start doing 53 and or 55. They're both at Calc Chat. 53's at Calc View. We'll hold up there and do the rest of them later. Okay? Good deal. You need to get going as soon as possible on differential equation? Huh?
That's great.
Oh yeah, we're going to have a break.
I'm saying y'all can have a lunch break. I'm just going to eat a banana and a protein bar.
Yeah.
So
I've even already eaten my apple. All I need to do is swap out books and get something to drink just because my throat is dry. But yeah, it's not going to be long at all. What you think?
10 minutes.
Okay. Let's try to be back by 10. I need to save this. Huh?